Hi, and welcome to the Earth SciShow podcast. I'm your host, Mr. Earth Guy, and today we are going to discuss an extremely important topic humans have likely pondered over ever since we developed a sense of time: the age of the Earth. But before we get started, please remember to follow us on this platform and leave us a review. Share this podcast with your friends who love science as much as you do. It really helps us grow our audience and keep the show going. Thank you so much for your support. The best scientific research to date suggests that our planet formed over 4.54 billion years ago. But before we get into the details on how this date is derived, let's look at the history of the search for the age of the Earth. Getting to the point of knowing Earth's age at such astonishing precision has been a long scientific journey. Physicist William Thomson, also known as Lord Kelvin, concluded in 1862 that Earth was between 20 to 400 million years old. He did this based on calculations of how long it took to cool from a molten state. His findings brought around a lot of controversy. For example, his calculations did not account for heat produced via radioactive decay. And in fairness to him, radioactive decay was an unknown process at that time. Geologists like Charles Lyell had trouble accepting such a short age for the Earth. For biologists, even 100 million years seemed much too short to be plausible. In Charles Darwin's theory of evolution, the process of random inheritable variation with cumulative selection requires great durations of time, and Darwin himself said that this did not seem like enough time for those processes to occur. It wasn't until the late 19th century and early 20th century that scientists discovered radioactivity, and more importantly, that radioactive elements such as radium produce enough heat to melt its own weight in ice in less than an hour. Geologists quickly realized that this upset the assumptions underlying most calculations of the age of the Earth, such that radioactive decay within the Earth meant that heat was sustained and it didn't slowly dissipate over time. With this newfound knowledge, they knew that the initial calculations by physicists like Lord Kelvin had to be wrong. Shortly after the discovery of radioactivity, further research by Ernest Rutherford, also known as the father of nuclear physics, and Frederick Soddy concluded that radioactivity was due to a spontaneous transmutation of atomic elements, stating that in radioactive decay, an element breaks down into another lighter element, releasing alpha, beta, or gamma radiation in the process. They also determined that a particular isotope of a radioactive element decays into another element at a distinctive rate. This rate is given the term half-life, or the amount of time it takes for half of the mass of the radioactive material to break down into its decay product. Some radioactive materials have short half-lives, some have longer half-lives. Uranium and thorium have long half-lives and so persist in the Earth's crust, but radioactive elements with short half-lives have generally disappeared. This suggested that it might be possible to measure the age of the Earth by determining the relative proportions of radioactive elements in the geological samples. Rutherford with colleagues was the first to attempt measurements of rocks in 1904, but instead of quantifying the differences in isotopic ratios between parent and daughter isotopes, he used helium, which is a byproduct of alpha decay. His assumptions were based on all helium being contained within the rock sample and not dissipating. This led to a false calculation of 40 million years. Another physicist, Burton Boltwood, continued this research by focusing on the end products of the decay series, trying to understand when radium would stop decaying and reach a stable state. He achieved this a year later in 1905, when he suggested lead was the final form. Rutherford joined in this research, and they speculated that the radium-lead decay chain could be used to date rocks and samples. Boltwood published this paper detailing these results, however at the time geologists didn't seem very interested. It wasn't until 15 years later, in 1921, that Arthur Holmes showed that radiometric dating was a valid method for aging rocks and suggested that the Earth was a few billion years old. Radiometric dating continues to be the predominant way scientists date geological timescales. Techniques for radioactive dating have been tested and fine-tuned on an ongoing basis since the 1960s. 40 or so different dating techniques have been utilized to date, working on a wide variety of materials. Dates for the same sample using these different techniques are in very close agreement on the age of the material. Now, it's possible that contamination problems do exist. However, by using different forms of decay chains on same samples and different isotope ratios, they can cross-check to ensure that there is minimal error. Today, the most commonly used isotope dating for Earth's age is uranium-lead dating. More specifically, the parent isotope uranium-238 decaying into the stable isotope lead-206. In order to date the rock, scientists measure the relative quantities of parent and daughter isotopes in their sample. From prior studies, they already know that the half-life of uranium-238, which is the amount of time it takes for 50% of the uranium to convert to lead, is around 4.45 billion years. Therefore, if the rock sample has 50% each uranium and lead, the rock is 4.45 billion years old. If the sample has 25% uranium and 75% lead, the sample is 9.5 billion years old. So now that we have an understanding of the history of radiometric dating, how do we go about finding the oldest materials on Earth? Earth hides its age very well. Today, most of the crust is younger than the planet, having been modified over Earth's history to some degree by plate tectonics and erosion. At subduction zones along continental margins, oceanic crust is pulled into the mantle and melted. Meanwhile, new crust forms at mid-ocean ridges and hotspots. Tectonic plates push against each other, creating mountains. Streams and rivers carry weathered rocks to lowlands and the ocean, depositing stones, mud, and sand along the way. Over geologic time, accumulated sediments can become compressed to form rock or pulled into the mantle to be recycled. Pristine, unaltered rock formations may be impossible to find, but there are still very rare ancient rocks to be found. Zircon crystals from Jack Hills in Western Australia aged at 4.404 billion years, currently holding the record for the oldest mineral on Earth. In northwest Canada's Acasta River, some rock samples are as old as 4.03 billion years. Zircons are used by geologists because they're some of the most durable crystals in the world. They are commonly formed in felsic igneous rocks such as granite. They can also be formed in metamorphic rocks. However, because the melting point of zircon is very high, some 800 degrees Celsius, these processes add new layers to the crystal rather than completely reworking it. Along with their very high melting temperatures, they are also chemically non-reactive. But more importantly, they contain small but measurable amounts of uranium, which substitutes for the zirconium in the crystal lattice when the crystal grows. These are the uranium isotopes 238, which we discussed previously, and uranium-235. And uranium-lead dating is a great candidate because lead cannot be incorporated into the crystal structure of zircons. Therefore, if lead is found in zircon, it only got there because it decayed from the uranium isotope within the crystal lattice. This prison-like property of zircon makes it an ideal mineral for dating rocks. Other rock samples have also been used, including moon rocks and meteorites. A lunar sample brought back by Apollo 14 astronauts had a fragment from our planet embedded within it. Scientists think that an asteroid impact violently flung pieces of Earth's crust into space, and at least one of these pieces landed on the moon. Studies found that fragment to be about 4 billion years old. Since ancient terrestrial rocks are not likely to be the leftovers of our planet's original crust, scientists needed to also look at old materials elsewhere in the solar system that had not undergone much change like the rocks on Earth. The moon's surface, despite a history of volcanic activity and meteorite bombardments, has a better chance of preserving crust dating to its creation. A study published in 2019 of rocks brought back by the Apollo missions suggests that the moon formed around 4.51 billion years ago, about 50 million years after the solar system's formation. Scientists have also looked at the remnants of meteorites with calcium-aluminium-rich inclusions. These were among the first bodies to coalesce as planets began forming around the young sun. They've been dated back to 4.56 billion years. Whilst the history of radiometric dating has been anything but smooth sailing, it has been proven time and time again to offer a conclusive and viable way to date the age of the Earth. And as we strive to expand our footprints beyond the realms of Earth and onto other planetary bodies, we will be able to use these exact techniques and processes to unravel the history of the solar system. That's all for today's episode on Earth SciShow. If you enjoyed this podcast and want to listen to more exciting geological stories of our planet and the universe, be sure to hit that follow button and watch out for the notification when we release our next episode. I'm your host, Mr. Earth Guy, and remember, stay curious.